Welcome back to part 5, which is the final part of this lecture. So here we discuss the theory of Brownian motion, which is usually discussed in the beginning of a lecture or a textbook on non-equilibrium statistical mechanics. But here we're going to discuss the standard topics like the Langevin equation and Einstein's theory of Brownian motion based on the modern approach that we have been developing. So this may be a climax or an anticlimax, you will see. Anyway, let's get started. So I will start by discussing typical experiments, but we have been talking about this several times. So consider a plastic bead of diameter like 1 micrometer, very small one. You cannot see it on your eye by your eye, but you can see it by using a microscope, and it's in water and at room temperature. So then water molecules around it have very high velocities, like 500 meters per second, and the size of the water molecule is very small, 3 times 10 to the minus 10 meter. You can never see this, even using a microscope, okay? And they are so small, and there are so many of them, and they are so fast. So you can just estimate that there occurs like 10 to the 90th collision per second, many collisions. And so because of this many collisions of water molecules, the bead exhibits a random motion. The Brownian particle exhibits a very special random motion, and that can be observed by an optical microscope. Okay, and this is called Brownian motion. And this is the trajectory of Brownian motion. So it really wiggles, and you get this kind of like fractal type pattern. And if you just skip some time, and then you get this kind of zigzag pattern, okay? And it is known that this Brownian motion shows a very peculiar behavior in which the displacement of the particle squared is proportional to time, okay? Usually, of course, if a particle has a velocity, the displacement is proportional to time. But in this case, squared is proportional to time. And okay, here is the actual plot of displacement squared versus time. And if you look at each data, you don't see anything, any regular behavior. But if you average like, I don't know, 5 samples, then you almost get a straight line showing this behavior. Okay, so this data were provided by my colleague Takayuki Nishizaka, who is a biophysicist. And okay, he also provided me the movies. So let's take a look at the movies. So these are movies taken by a microscope. And this shows, which, do I have point? Okay. Here you have, this is a real-time view of Brownian particles, plastic beads. And this is real, the size is like 60 micrometer, 50 micrometer, very small. And, you know, these big ones are not big particles. I mean, it's out of focus and becomes big. So it shows this kind of wiggling motion. And here, Takayuki showed basically the same thing, but but he magnified this by 7.1 times. But at the same time, he slowed this down by factor 50. Okay, and then we see that this motion and this motion are basically qualitatively are very similar with each other. So this shows this particular scaling behavior of Brownian motion, because, you know, 7.1 is actually the square root of 50. Okay. Okay, so this was the movie. So let's go back to the lecture, handwritten lecture. So now we want to develop a theory of this kind of motion of a plastic bead surrounded by many particles. But we are used to that because we had similar consideration in part 1. I think you remember. Okay, so now the notation is almost like part 1. So we go back to the treatment based on classical Hamiltonian mechanics and equilibrium statistical mechanics. So X denotes the phase space point of everything, including the bead, the plastic bead, the Brownian particle, and all the water molecules, many water molecules. And of course, our P denote the position and momentum of the bead. So it lives in, for example, R3 and also R3. And this XW describes the water molecules. So it's a collection of all position and momentum of many, many, many water molecules. And so this is the total Hamiltonian. It's a sum of the Hamiltonian of plastic bead, Hamiltonian of many, many water molecules, and the interaction part. We assume that this is time reversal invariant. Okay, so these are almost the same as in part 1. Here comes a slight difference. Let S be an arbitrary finite region in the phase space of the bead. So now we did not consider momentum of this particle before, but now we also look at the momentum of the bead of the Brownian particle. So this is the phase space region like this. And this one is new. For this region, we denote by S star, it's time reversal. It means that you don't change R, but you just flip the momentum. It looks like this. And this is, I think, familiar notation. Chi Sx is 1 or 0, depending on Rp. Of course, Rp is the component of this X. Okay, so if you look inside X and if you find Rp is in S, then it's 1. If Rp is not in S, it's 0. Okay. Then we consider the detail balance condition as we did in part 1. For that purpose, we again define the restricted partition function. So without this is just a partition function of everything at the inverse temperature beta, but we here have this characteristic function. So its condition, we impose a condition that the Brownian particle, the bead, the phase space point of the bead is in this S. Okay. And now we consider the following transition probability. So tau is a positive time, and we consider two arbitrary regions, S and S prime, in the phase space of the bead. And then this probability is defined like this. So what is this? Well, here we have the canonical distribution. Canonical distribution of the whole phase space point at inverse temperature beta, but actually the normalization was a bit different. I'm sorry. So, but with this restricted partition function. So this one describes the restricted canonical distribution. Okay. So everything obeys the canonical distribution, but with a restriction that the bead, the phase space point of bead, is in S. Okay. And now here we have another characteristic function, which says that this is a time evolution operator. So if the initial state is X, then at time tau, this describes the phase space point of everything. But this says that the phase space point of the Brownian particle at time tau is in this phase space region S prime. So you start from S and it goes to S prime. This is a probability that the state of the bead in S is in S prime at time tau, final time tau, provided that the whole system is initially in equilibrium with the constraint that the state of the bead in S. Okay, this is the meaning. Okay, now we argue that this transition probability satisfies this symmetry. That's the detail balance condition, and derivation is exactly the same as that in part 1, page 32. But there is a difference. There is a difference. Since we consider the phase space region, including the momentum part, here we have transition probability from S to S prime. But here we don't have S prime to S, but we have S prime star to S star. Probably it's clear from this picture. Now we have momentum. So you go from here to here. So this shows that your velocity is positive, right? And if you want to go back directly from here to here, that's very hard because you have to flip your velocity. But from going from here to here, it's quite natural. So it's very natural that you should think about this mirror image, time reversed image, and consider this process. Okay. And the derivation is actually very, very similar, almost exactly the same as what we had in part 1, page 32. Let's look at part 1, page 32. Okay, so probably you recall this. It's a very simple proof, but you simply use symmetry and switch between initial and final into. And in this case, we were considering only the position part, so we didn't have to worry about taking star. But now in this new consideration with S, you have to be careful about taking a star. So if you do that carefully, then and repeat this derivation, you will get this. So it's so simple, but I encourage you to try that, but it's very simple. Okay, so this is a detailed balance condition obtained in this situation, and this is a rigorous result. Okay, exact result. Now we want to further argue that this with some plausible assumption we can further restrict the form of this transition probability in like this. Okay, so what we are going to consider is that we first suppose that this transition time tau is very, very small, very small. And then in this case, this wiggling particle does not move, essentially does not move. So we can safely assume that there is no change in the position r, and only the momentum p changes because of the collision with water molecules. Okay, so we take S as a very small region, including Rp, and S prime to be a very small region, including the same R and different P prime. Okay, and then we first look at this ratio of the restricted partition functions. Okay, so this is the definition. And here, of course, you have Hamiltonian, and within Hamiltonian, this. But in this case, the only relevant part is this, and kinetic energy of the Brownian particle. Okay. Everything else is basically the same when you integrate, because R is the same. Okay. And so what do you see is that this ratio is just given by this, and here you have the difference in the kinetic energy. So for sufficiently small tau in which we can neglect the change of R, we have derived almost rigorously this symmetry. Okay? This transition probability satisfies this very simple symmetry. Now we further argue that if P is written in a simple form of exponential times some function of kinetic energies, then it must be written in this form. Okay. Of course, you can think about much more complicated form, but the simplest form you can think about is this. Okay, and here alpha is any constant, Okay, and to show that this satisfies this, you simply plug this in here. It's very simple, and of course you have to take this star, but this is just switching the sign of momentum, but you have this absolute value, so it's almost nothing. So you simply plug this in here, and you see that this is satisfied for any alpha. Okay, but I want to further argue that alpha it's reasonable to take alpha to be 1/2. Recall that in similar situation in which we jump from one value to the other, then we actually took alpha to be 1, and so we didn't have this. Okay. So this was the natural form when we consider this kind of transition. But now we are considering totally different situation. We are considering very small change of momentum in very, very short time. And I argue that in this case, alpha of 1/2 is natural. Why? Well, think about the limit when P is equal to P prime. Okay, so it means that no change takes place. Of course, it's very small. But, unless alpha is 1/2, this transition probability still depends on P, even if you set P equal P prime. If you set P equal P prime and you compute, you get like 2 alpha minus 1 times, anyway, it depends on P. But it's weird. I mean, it should be something independent of P when P equal P prime. P equal P prime means nothing takes place. So depend on this consideration, I take alpha to be 1/2. Then we see that this becomes very simple like this. And here you simply have the difference in the square of P and P prime. Okay. Absolute value square of P and P prime. This is a very simple natural form. And in terms of V, velocity, this can be written in this way. Okay, so I won't say that we have derived this form, but I would say that we have argued that this is very natural and probably the simplest, most natural choice of P. And okay, but we derived this. I want to stress that we have derived this symmetry. Okay, so there's nothing wrong about this. So we can trust this. And then we asked what is the most natural simple form of this which satisfies this relation, well, I argue that it's this or this. Okay, and of course, based on this assumption, we will derive a very simple stochastic process that can be tested against experiments. So, and that confirms this choice. Okay, so we have determined the form of this transition probability. Now let's proceed to consider the corresponding stochastic process, which is called the Kramers equation, and it determines the time evolution of the probability density P, P of the phase space point of the Brownian particle. But actually, instead of using P, let me use V. Okay, this is the position and the velocity of the bead. The reason is basically we have too many P's. That's confusing. So let's use the velocity V. Okay. Now, so our phase space point is described as X and V. And for simplicity, for notational simplicity, let's consider the one-dimensional case. Okay, so this will be XV. Okay, and we first focus on the effect of collisions of water molecules. And then, of course, X doesn't change for a short time. So we only focus on the probability density for V. And to analyze this, we want to make a theoretical simplification or an idealization, and we consider a discretized system. Okay, we first assume that our V, the velocity V, is always written like this: J, an integer, times delta, a very small positive constant. And also time t is written as n, an integer, times a very small positive constant epsilon. This is very, very artificial, but this makes the game easier. And of course, we finally take the continuum limit in which delta and epsilon go to 0. Okay, and so then we can talk about the probability. So PVT is the probability that the velocity is v at this discrete time t. And then as time is discrete, so as time proceeds by one step, and so as time t changes to t plus epsilon, we assume that the velocity may change. Velocity may not change, but if it changes, it only changes by plus delta or minus delta, the smallest units. Okay, so I know that this is very simple and too simple. And you might wonder, why doesn't it change by plus 2 delta or minus 3 delta? Or yeah, that's possible. So you can think about, you can consider much more complicated model in which V can change by like 50 times delta with some probability. But you know, even if you do this, consider this kind of complicated system, there is some sort of central limit theorem type mechanism going on, and you finally get exactly the same result in the continuum limit. So you don't have to worry too much about the simplicity of the model. So we only consider the simplest model in which we can change by plus or minus delta. Okay, now then we only focus on this transition probability in which V goes to V plus delta or V minus delta. And we can identify this with P tau SS prime with suitable choice of tau, suitable choice of S and S prime, which we were considering. So we know this form, okay? So we know that this is written like this. Okay, now we consider the master equation that this PVT obeys. So, well, probably this is not necessary, but let's go back to part 2, page 29, where we consider the master equation for a Markov jump process. So this is the beginning of master equation. Here we consider the change in the probability that the system is at J. And then we argue that this change is given by the sum of two terms. The first term is the escape. So this is this shows the process that you are in V, you are in J at time t, and then you escape to different states. And so you have minus. So this is the positive part. You were in different state k at time t, but you jump into J. Okay, so we do exactly the same thing here. We consider the difference here, and the difference is given by, first of all, this is a -1. This is the escape. Your velocity was v at time t, but you will it will jump. We will jump to nearby v plus nearby velocity v plus delta or v minus delta. So you have minus sign here. So these are jump ins. the velocity was v plus delta at time t, and it jumps in. And okay, this is a similar one. Okay, so this is our master equation. So we want to plug in the explicit form of p here. So we look at this explicit form we obtained in page 4. So actually, we don't need to recall page 4. I have written it here. So instead of v prime, I wrote it v plus minus. And this is just a tedious calculation. I expand, and yes. And now, since delta is very small, I would like to expand this in delta to the second order to get this. And also this one, I did the same calculation to get this. Okay. And now we kept everything up to order delta squared, but this order delta squared actually always comes with 1. Okay? And this means that this is always absorbed in this one, and this can be neglected safely. So I will neglect this. Okay, so I will only consider this part. Now, I substitute this into the master equation here, this one. Okay, so the left-hand side is simply this. The right-hand side, first I consider the escape one. So escape, for the escape thing, you want to sum this plus 1 and minus 1. So you sum these two, so this one cancel, and you have twice, and you get this. Okay, and these are coming in. So this part you just here you count the probability from v plus delta to v. So you have, you don't have minus, and you have this times this, and a similar one with v minus, so we have minus. Okay, so this is everything. Plus order delta cubed, I omitted that. And now I want to rearrange this according to the power of delta. First, I consider the terms without delta. So we have minus 2 PV, it's here. And here, this is PV plus delta times 1 times PV minus delta. So we have this. Now I want to consider terms which is proportional to delta. It's here and here. We have minus sign, so we have this difference here. Finally, I collect terms with delta squared everywhere. But this becomes positive. They all have the same sign, and we get this. Now we will take the continuum limit in which epsilon and delta become small. So we should examine the epsilon and delta dependence of these terms. And this one is trivial. So we have very small difference in time. So this will be epsilon times p dot, okay, roughly, if your epsilon is small. Okay, now here, when delta is very small, you see that this is basically the twice derivative. Okay, so this is what do you say, twice difference or whatever. But anyway, so if delta becomes 0, this becomes delta squared times the twice derivative. Okay, and this one here, it's easier. This becomes the difference is 2 delta. So when delta is small, this becomes 2 delta times the derivative. And here, when delta is small, nothing is wrong. This is simply 4p. And this is a good news. So here on the left-hand side, you have epsilon. On the right-hand side, here you have delta squared. Here you have delta, explicitly delta, and this here you see it's delta. So again, it's delta squared, and you have delta squared, and this is nothing. So now everything, the leading term of these things are all proportional to delta squared. And here you have epsilon. So this motivates us to set this constant a like this. Okay. Ooh, did I say anything about the constant? Okay, probably I didn't say anything. So of course, here a is a constant, which is independent of p and p prime. Okay, of course, so a may depend on many things, tau, s prime, right? Okay, but anyway, it doesn't. I said it's constant. Did I say? But it's a constant in the sense that it doesn't depend on p and p prime. Okay, so now we choose this constant as some constant times epsilon divided by delta squared. Right? Then this will probably this will take care of these small factors. Okay, so I think we are basically ready. So we write A like this. So this is the constant. And of course, you can write a constant in any form, but here gamma is some new mysterious constant, but m is the mass of the Brownian particle, and beta is the inverse temperature. So there is no reason that you can write it like this. And I would say that this is not justified for the moment, and it will be justified later in page 16. So we have to wait for a while. So please remember that we are not justified yet to take this, but we will be justified later. But anyway, so we assume this form of A, and we substitute this into page 3 of page 6. It means this one, no, this one. Okay. Yeah, we substitute this form of A into this, and just trust me, if you rearrange everything, we get this very nice form. And now we can easily take the limits where epsilon and delta go to 0. Oh, but we have to be careful. PV itself is the probability. So if you divide this by delta, you get probability density, right? Of course. And so the limit of this will be the probability density for V. So actually, to be precise, I have to divide everything by delta. But anyway, this shows you that it has a very nice form. And if you take this limit, this converges to this partial differential equation. Okay, and this becomes actually this divided by delta becomes this. This divided by delta becomes this twice derivative. This becomes this first derivative, and this becomes this. Now you have these terms, and it happens all the time, but you can combine this into one formula like this. Okay, so now we have found that the effect of collisions of water molecules can be described by using this partial differential equation. Okay, now we can write down the final form of the Kramers equation, but we should recall that this we are only considering the effect of collisions, but this Brownian particle, of course, obeys the Newton equation or the Hamiltonian dynamics. So this probability density, of course, changes according to the deterministic Hamilton dynamics, but this was already considered back in part 1. So we know that this probability density obeys Liouville's equation. Okay, and what was Liouville's equation? Let me go back to part 1, page 12. I'm sorry, this is a kind of mess. So the notation is slightly different. So this is Liouville's equation in the most general form, but if you write it in the Hamiltonian mechanics case, you get this. Okay, so this is in 3 dimensions, and you have n particles, and also I'm using P instead of V. I'm sorry, I didn't predict that I would use V here. But anyway, if you carefully consider the case with 1 particle, 1 dimension, and you rewrite P by using V, it's not very difficult. This will be V and V. And, okay, and so you just need some M's. Yeah, so you get this form. Okay, and F is the external force to the particle. So in the case of potential force, it is written like this. Okay, so this is Liouville's equation that we derived in a messy form in page 12 of part 1. Okay, so this takes care of the deterministic Hamiltonian dynamics, and we have seen that this takes care of the collisions of water molecules. So you simply add these terms to get the final form. Okay, so this is called the Kramers equation, and it describes the time evolution of the probability density, describing the phase space point of a Brownian particle. Okay, did I say it correctly? Anyway, you know it. Okay, so it's a bit complicated, but this part is Liouville's equation, and this part with gamma describes the effect of collisions. Okay, and this, of course, was 1 dimension, but if you go to 3 dimension, 1 particle, you get this. Well, this is the rewriting is basically the basically trivial. And actually, we had this before. And here, this second derivative should be Laplacian. And this part is this. Okay, so we have we started from detailed balance type conditions consideration. We started from the mechanics of Brownian particle and all these water molecules, and we used equilibrium statistical mechanics. We made this detailed balance type condition, or actually fluctuation theorem type consideration to derive detailed balance condition, and with plausible assumption about transition probability, we have derived this Kramers equation.